All right, folks, gather round, because NASA just dropped another alert about our favorite cosmic wildcard, Comet 3I/ATLAS. And honestly, at this point, trying to predict what this thing will do next is like trying to nail down smoke in a hurricane. Every single time we think we've got it figured out, every time the data starts making sense and we're ready to draw some neat conclusions, a fresh batch of observations comes rolling in and flips the entire script sideways. This isn't your grandma's predictable comet, folks. 3I/ATLAS is rewriting its own story with every mile it travels through our solar system. And today's update. It might just be the strongest hint yet that we're witnessing something truly jaw-droppingly unusual unfold in real time. So what exactly triggered this latest NASA alert? And why is everyone suddenly buzzing like a supercharged nebula? Well, this time the shift wasn't just some pretty new feature popping up in images or a slight twinkle in its brightness. Nope. This shift showed up first, subtly almost ghost-like in its orbit. Here's the geeky but cool breakdown. Overnight telescopes worldwide, using the exact same methods, fed a fresh batch of super-precise position measurements into our orbit calculation software. Nothing changed in how we observed it, but when those new numbers got plugged in, something just didn't click. The residuals, those tiny differences between where the math said the comet should be and where we actually saw it, started acting seriously weird. Normally these differences are random, like scattered dust motes, but this time they weren't just bigger. They lined up pointing in a distinct new direction. That, my friends, is a cosmic alarm bell. It screams that the comet's fundamental motion has changed. Now, if that wasn't wild enough, the universe in its infinite wisdom decided to give us a second completely independent confirmation. While the orbit team was scratching their heads, the imaging team finished processing a separate set of high-contrast pictures of the comet's inner region. And what did they show? The exact same story. Last week, we saw a stable pattern, a clear inner coma, and a dominant main jet. But today's images. The inner coma, that bright fuzzy halo, is skewed in a slightly different direction. The main jet, the comet's most prominent exhaust stream, has undeniably tilted, leaning into a new position compared to last week. Even the smaller secondary streams have rebalanced, and the comet's tail has developed a subtle S-curve that simply wasn't there before. Two independent lines of evidence, orbital mechanics, and direct observation, both screaming, shift. 2. This isn't a coincidence. It's not a data error. It's a real physical transformation happening right now before our very eyes. This comet is actively changing how it's venting, which changes how it's pushing itself, which changes its orbit. And that, dear cosmic enthusiasts, is why NASA's got a cosmic headache today. So why is this thing acting like it's got a mind of its own? To truly grasp the antics of 3I/ATLAS, we need to talk about what comets actually are. Forget solid rocks. Imagine them more like colossal dirty snowballs, or better yet, a fragile frozen pile of cosmic rubble. Their core, the nucleus, isn't some monolithic chunk. It's a delicate concoction of volatile ices, water ice, carbon monoxide, ice, carbon dioxide, ice, all mixed with dust and rocky grains barely held together by its own weak gravity. Now, as our intrepid 3I/ATLAS swings closer to the sun, that ice starts to warm up, but not evenly. The sun's heat slowly seeps through the dark, radiation-processed crust, reaching those deeper pockets of ice. What happens next? Sublimation. That's when ice turns directly into gas, skipping the liquid stage entirely. This gas builds up immense pressure beneath the surface until, bam, a crack forms a weak spot, gives way, and suddenly you have a jet-high-pressure gas and dust blasting into space at hundreds of meters per second. And here's where Newton's third law of motion makes a dramatic entrance. For every action, there is an equal and opposite reaction. When that material shoots off in one direction, the comet gets a tiny but persistent push in the opposite direction. We call this a non-gravitational force, and it's essentially like a tiny, erratic rocket engine constantly firing, nudging the comet off the path pure gravity would dictate. For months, we thought we had 3I/Atlas's rocket engine pretty well characterized. We knew its direction, its strength. But today, to make the new observations fit, that push, that thrust vector, has to be tilted in a different direction. Why? What could cause such a dramatic reorientation? Well, there are two primary theories swirling around, and honestly, it's probably a bit of both. Possibility number one: a brand new vent just ripped open. Picture this. The comet's surface is a patchwork of old fractures, sealed vents, and hidden pockets of ice at varying depths. As the sun's heat finally percolated down to a previously stable buried pocket of volatile ice, the pressure reached a critical point. Pop. A new jet bursts through a fresh location on the nucleus, perhaps stronger than existing ones, or just in a totally new direction. If this new jet is powerful enough, it could completely reorient the net non-gravitational push on the comet, explaining the orbital shift and the new visual configuration. It's like adding a new powerful thruster to your spaceship. But wait, there's another perhaps even more intriguing possibility. What if the entire nucleus is changing its spin? You see, those jets don't just push the comet, they also apply torque, a twisting force. Think of an ice skater spinning. Extend their arms, they slow down. Pull them in, they speed up. A comet's jets firing at weird angles are constantly applying tiny torques to the nucleus. We already suspect 3I/Atlas isn't spinning like a perfectly stable top. It's likely tumbling or precessing, slowly wobbling its spin axis. If its spin axis is precessing, then the orientation of its existing vents in space changes over time, even if the vents themselves aren't new or changing their output. The whole object just tilted. So today's shift could simply be another step in that ongoing cosmic wobble with existing jets now pointing in a different direction due to the nucleus's reorientation. Either way, this cosmic snowball is full of surprises. Now here's where the story of 3I/Atlas takes a slightly more unsettling turn. We've talked about the dirty snowball analogy, but let's be even more direct. The nucleus of this comet is incredibly fragile. It's not a solid chunk of rock. Think of it more as a loosely held pile of ice dust and rock, barely clinging together under its own incredibly weak gravity and some minor cohesive forces. It's like a cosmic house of cards, constantly under internal stress, every time one of those jets fires. Every time a new vent opens, every time the spin axis tilts even slightly, you're not just altering its trajectory, you're fundamentally redistributing the stress inside this precarious object. Imagine a jet blasting material off one part of the surface changes the mass distribution. This, in turn, alters how all the internal forces balance out. Parts of the surface previously shielded suddenly get exposed to sunlight reflecting off other parts of the comet, causing uneven heating. Stable cracks can suddenly be pulled or compressed in new, unforeseen ways. Cavities within the nucleus that were in a delicate equilibrium might get stressed and strained in directions they weren't before. In the short term, over days or weeks, these are just shifts. Interesting dynamic requiring new orbital solutions. But are they dangerous? This is where the worrying part kicks in. Over longer timescales, over months of repeated cumulative changes, all those shifts in internal stress start to add up. Each new configuration, each burst of activity, is another load, another test of whether this fragile nucleus can truly hold itself together. And here's the kicker: we've seen this before right here in our own solar system. Comets often follow this pattern: subtle changes in non-gravitational forces, evolving jet structures, sometimes even slowly increasing rotation rates as the jets spin them up. And then sometimes, without much warning, a sudden catastrophic breakup. The nucleus simply can't absorb any more stress. Something finally gives, and the entire object disintegrates. It might split into a few large pieces, or it might just crumble into a spectacular cloud of fragments and dust, ceasing to exist as a coherent body. Now, let me be absolutely crystal clear. No official NASA alert is screaming, 3I/Atlas is about to explode. The language in these updates is always painstakingly careful, very technical. They talk about new updates to the orbital solution, measurable evolution in the outgassing direction, or a shift in the net non-gravitational acceleration. Very precise, very measured. But here's the insider perspective. You don't schedule extra telescope time. You don't push observatories to collect denser data more frequently. You don't send out internal alerts to other research groups because you think everything is just fine and dandy. You do all that because you know something profoundly interesting is happening. Something that could develop into something far more significant. It's because this object is active in a way that truly matters, in a way that could lead to something entirely unexpected. So while no one is officially predicting a cosmic implosion, the scientific community is definitely holding its breath, watching this ticking iceberg with rapt, nervous attention. But beyond the immediate drama of its unpredictable shifts, 3I/Atlas holds an even more profound significance. It's not just any comet, it's an interstellar comet. Let that sink in for a moment. This isn't one of our local cosmic neighbors born from the same primordial cloud as our sun and planets. Oh no, this visitor is a genuine stranger in a strange land. It originated from another star system entirely, perhaps billions of years ago. Imagine it forming around a different sun in a completely different planetary nursery, then being ejected into the vast, cold, dark emptiness of interstellar space. For unimaginable epochs, it drifted frozen solid, completely dormant, silently tumbling through the void. And now, for the very first time in its existence, this interstellar vagabond is having its one and only close encounter with our sun. Think of the implications. Every single bit of its current wild behavior, the constant venting, the shifting jets, the wobbling nucleus, and yes, even the potential for breakup, is literally a live experiment playing out before us. We're observing in real time how an object from another star system reacts to the intense heat and radiation of our star. What does its volatility tell us? How strong or fragile is its internal structure? What can its composition, inferred from its outgassing, reveal about the conditions in its distant birthplace? The answers to these questions are nothing short of groundbreaking. Its observed behavior teaches us invaluable lessons about comet formation and composition in completely different stellar environments than our own. Are comets like 3I/ATLAS? Common across the galaxy, do other star systems produce these same dirty snowballs with similar mixes of ices and dust? Is its propensity for sudden shifts a common trait for all comets, or is it unique to interstellar travelers? This object is a direct, tangible sample of exoplanetary building blocks, giving us insights into the early chemistry and dynamics of a system light years away. It's a literal cosmic messenger, delivering tales from a foreign sun to our doorstep. We're learning about the strength, the density, and the volatility of an alien object. A piece of another universe right now. The data we collect from 3I/ATLAS isn't just about this one comet. It's about understanding the very fabric of the cosmos and how planetary systems, including our own, come into being. This cosmic headache is actually a treasure trove of interstellar secrets, offering us a fleeting, unparalleled glimpse into the universe beyond our solar system. So what's the cosmic bottom line here? The bottom line is that 3I/ATLAS is far from done. It's not just quietly coasting out of our solar system on some fixed, predictable path, waving goodbye. Oh no, this interstellar rebel is still very much in the game. Still burning, still venting, still actively adjusting its own motion. Layer by layer, vent by vent, rotation by rotation, day by day. Yesterday's shift wasn't the final word. Today it shifted again. And if that pattern continues, if every new orbital solution demands a different thrust direction, if every new set of images shows those jets leaning just a little bit further, a little bit harder, then what we're watching here is truly a live front-row experiment in cosmic dynamics. The big question that hangs in the cold vacuum of space is this: will 3I/ATLAS stabilize as it retreats from our sun? Or will the accumulated stress of its dramatic encounter prove to be too much for its fragile structure? Will it hold itself together, or will it succumb to the forces tearing it apart, giving us a spectacular, if unfortunate, breakup event? The uncertainty is precisely what makes this object so captivating and so vitally important to observe. That's why observatories around the world are dedicating precious telescope time, tracking its every nuanced move. Every tiny shift, every subtle change in its tail, every fluctuation in its brightness holds the potential for a massive revelation about how interstellar objects behave when they finally meet a star after billions of years of silent wandering. This comet is a fleeting window into the secrets of other star systems, and we're getting a once-in-a-lifetime chance to study it up close. So keep your eyes on the skies, or at least on the scientific updates, because the story of 3I/ATLAS is far from over. It's a cosmic cliffhanger, and we're all waiting to see what happens next. What do you think will happen to 3I/ATLAS? Let us know in the comments below.